Hello to everyone. Welcome to the course on numerical linear algebra application. Now we are going to have 40th lecture of this course. In continuation to the previous lecture, we would like to learn some concepts related to the convergence of iterative methods. How iterative methods would be useful for real life applications. The Gauss-Seidel method for a symmetric positive definite matrix. We show that the Gauss-Seidel method converges with an arbitrary choice of x1 for a symmetric positive definite matrix. So if the matrix is symmetric positive definite, then it converges for any arbitrary choice. Let A be a symmetric positive definite matrix, then the Gauss-Seidel method converges for any arbitrary choice of the initial approximation x of 1. So the proof is as follows. Because A is symmetric, we have the coefficient matrix A is equal to L plus D plus L transpose, where L is the matrix defined as L is equal to 0, 0, 0, 0, A21, 0, 0, 0, AN1, AN2, AN minus 1, 0, where the diagonal is D is equal to A11, A22, ANN. And B Gauss-Seidel is minus of D plus L whole inverse L of transpose. We will now show that the row of BGS is less than 1 and minus lambda B an eigenvalue of BGS and U be the corresponding eigenvector. Then D plus L whole inverse multiplied with L transpose of U is equal to lambda of U. Multiplying the last equation to the left of both sides of D plus L and then U star, we get as U star times of L transpose U is nothing but lambda times of U star D plus L of U, or you can write it as U star AU minus U star L plus D of U is equal to lambda times of U star L plus D of U, since the matrix A is equal to L plus D plus L transpose. L plus D plus L transpose. Or we can write it as U star AU is equal to 1 plus lambda times of U star L plus D of U. Taking the conjugate transpose on both sides, we will have U star AU is equal to 1 plus lambda bar U star L transpose plus D transpose times of U. Adding 1 and 2, we obtain 1 over 1 plus lambda plus 1 over 1 plus lambda bar multiplied with U star AU will be equivalent to U star L plus D plus L plus D times of U plus U star times of L transpose plus D transpose acting on U. So you will have U star times of L plus D plus L transpose D transpose acting on U will be equivalent to U star A plus D transpose multiplied with U. So which will be U star A plus D acting on U greater than U star AU. So note that since A is positive definite, so is D, therefore U star D of U is greater than 0. Dividing both sides of last equation by U star AU. So you will have 1 over 1 plus lambda plus 1 over 1 plus lambda bar is greater than 1. So you will have 2 plus lambda bar divided by 1 plus lambda bar is greater than 1. Let lambda is equal to alpha plus I beta, then lambda bar is equal to alpha minus I beta. From equation 3, we then have 2 times of 1 plus alpha divided by 1 plus alpha whole square beta square is greater than 1. From which it follows that alpha square plus beta square is less than 1, that is rho of BGS is less than 1 since mod of lambda is square root of alpha square plus beta square. The rate of convergence and a comparison between the Gauss-Seidel and Jacobi method is, we have just seen that for strict row diagonally dominant matrices, both the Jacobi method and Gauss-Seidel method for an arbitrary value of x of 1. The question as to whether this is true for some matrices as a natural case. So how actually you can ensure the convergence faster? From our discussion in the last lecture, we know that it is the iteration matrix B that plays a crucial role in the convergence of iterative method. More specifically, from the proof of iteration, then we can write it as E of k plus 1 will be equivalent to error between k plus 1th step will be equivalent to x minus x of k plus 1. So E1 is equal to initial vector so x minus x of 1 related by this expression, norm of ek plus 1 is less than or equal to norm of bk times of norm of E1. Thus, norm of bk gives us an upper bound of the ratio of the error between k plus 1 step and initial error. Now we define norm of bk is less than 1, then we can have minus ln of norm of bk upon k is called the average rate of convergence for k iterations, and the quantity minus of ln of rho b is called the asymptotic rate of convergence. If the asymptotic rate of convergence of one iteration method is greater than that of the other, both methods are known to converge, then with larger asymptotic rate of convergence we will have faster. The following results on the rate of convergence of the Jacobi and Gauss-Seidel method can be proved. If rho is less than rho of bj less than 1, then the asymptotic rate of convergence of the Gauss-Seidel method is larger than that of the Jacobi method. If matrix A has all its diagonal entries positive and off diagonal entries non-negative, then the Jacobi and Gauss-Seidel method either both converge or both will diverge. When both methods converge, the Gauss-Seidel method convergence is faster than the Jacobi method. Note that we are talking about the asymptotic rate of convergence, not the average rate of convergence. Unfortunately, in the general case, no such statements about the convergence and the asymptotic rate of convergence of two iterative methods can be made. In fact, there are examples where one method converges but the other diverges. However, when both the Gauss-Seidel and the Jacobi method converge, because of the lower storage requirement and the faster rate of convergence, the Gauss-Seidel method should be preferred as compared to the Gauss-Jacobi method. And when you talk about the convergence of the successive or relaxation method, it depends upon the choice of the relaxation parameter. Omega is relaxation parameter. It is natural to wonder what is the range of omega for which SOR iteration converges and what is the optimal choice of omega. To this end, we first prove that the following important results which were developed by Kahan in 1958. For the successive relaxation to converge for every initial approximation x of 1 in the interval 0, 2, we recall that SOR method, successive relaxation, which will be given by d plus omega L whole inverse multiplied with 1 minus omega times of d minus omega of u, where this L is A is equal to L plus D plus U. The matrix D plus omega L whole inverse is a lower triangular matrix with 1 over I is equal to 1 to n as the diagonal entries, and the matrix 1 minus omega times of D minus omega of U is an upper triangular matrix with 1 minus omega times of AII, that is I is equal to 1 to n as the diagonal entries. So, since the determinant of a matrix is equal to the product of its eigenvalues, we conclude that rho of BSOR is greater than or equal to 1 minus omega, where SOR is the spectral radius of the matrix. Since by the theorem we know that rho of BSOR has to be less than 1, we conclude that omega lies 0, 2. Let A be a symmetric positive definite matrix and omega lies between 0 to 2, then the successive relaxation method will converge for any arbitrary choice of x of 1. So there are certain classes of matrices such as consistency, ordered and two-cyclic matrices with non-zero diagonal entries was developed in the year 1971 and 72, and also by R.S. Varga in the year 2000. So the block diagonal matrices with non-singular diagonal blocks, such matrices, they show the block tridiagonal matrix arises in discretization of Poisson equation. So for example, if you look at OPT is nothing but 2 upon 1 plus 1 minus sigma beta j square. Furthermore, for consistency ordered two cyclic matrices, Jacobi method converges, so does the Gauss-Seidel method. And the Gauss-Seidel method converges twice as fast as the Jacobi method. Now if you take this example, look at this. 1, 2, 3, 4, 5, 6. 6 rows. 1, 2, 3, 4, 5, 6. 6 by 6 matrix. Look at over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So zeros are 14 and non-zeros are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that means non-zero entries are dominating. So it is not actually a sparse matrix. It is a little bit close to the dense matrix. Whereas this matrix is a sparse matrix. Now since A is strictly row diagonally dominant, look at here. 4 is greater than all these elements. 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 So we'll have, with 5 iterations of omega, you do get this convergence to exact solution as shown over here. So basically the successive relaxation method will give you the exact solution and up to 4 significant digits. Now with the same starting vector x of 1, the Gauss-Seidel method requires 9 iterations. So whereas in the previous case, we did it only 4 significant digits and it requires only the 5 iterations. So it requires 5 iterations. Whereas in this case, it requires 8 iterations over the symmetric successive relaxation method. There exists a symmetric version of SOR method which is derived by combining the SOR method. So you do get a matrix of this form. That is D plus omega U whole inverse omega L, and this omega is the parameter. Omega is the relaxation parameter and D is the diagonal matrix and L is the lower triangular matrix. And when you compare these classical iterative methods, so Jacobi method, easy to use, converges with an arbitrary initial guess, is guaranteed if A is strictly row diagonally dominant, as we have seen in the previous case. And Gauss-Seidel method typically converges faster than the Gauss-Jacobi method. Convergence with an arbitrary initial guess is guaranteed for the strictly row diagonally dominant and symmetric positive definite matrices. So today we have learned the convergence of the iterative methods. And if you look at this successive relaxation method, when omega is greater than 1, which is the relaxation parameter, is typically faster than Gauss-Seidel, the speed of convergence depends upon omega. Guaranteed convergence for a symmetric positive definite cis matrix, optimal omega is available for certain class of matrices such as the block symmetric positive definite matrix arising in Poisson equation. So these Poisson equations especially arises in fluid dynamics, and you can have a convergence by using successive over relaxation method. So in the today's class, what we have learned is basically how the iterative methods would be useful, how fast they are all as compared to Gauss-Seidel method, Gauss-Jacobi method and successive relaxation method with different relaxation parameter. So I will stop over here. Thank you very much for listening to my lecture and thank you once again.